So good morning, and thanks for being here. This is the webinar that we're going to have on compositional joint inversion in a multi-well framework. I'm Joaquin Ambia, and most of you already know me. Let's get right into it. The objective of what we're going to be doing today is to estimate petrophysical properties using 3D UTEP wells, which is the main objective of UTEP wells, or the main objective of the industry. We're just going to propose a specific pathway to do that. We're going to start with well logs, and at the end, we're going to get petrophysical properties. We're going to demonstrate a probabilistic strategy, which is one of the things that's going to make it different. Don't be scared by the word. It just means that we're going to have confidence intervals. That's it. It's easy to handle. We've made everything very easy to work with the inputs and the outputs. It should be very intuitive. And if you have any questions, by the way, if you want to speak up, just go ahead. There's a couple of sections where I left some gaps for questions, but if you have a question in the middle, it's fine to just ask. And while we're getting probability distributions and confidence intervals, I'm also going to show you a couple of new developments and all tricks using UTEP wells. First, a brief description of the strategy. We're gonna start with the field logs. In our case, it's going to be resistivity and the nuclear pack. We're going to invert for them to get physical properties. This means turning the log into a blocky log. That's what most people would think of. It's just the Earth model. And then we're going to use those to jointly invert for a composition for petrophysical properties. So that's going to be porosity, water saturation, shale concentration, and the compositions, nothing else. Fluid and mineral, both. There was something, okay. Somebody was waiting to get in, it's in. Now, continuing with that, before I even start doing this, we're gonna be working with a synthetic model, and I'm gonna show you how I built it. This is the reasons are twofold. One of them is there's a lot of little things in UTEP wells that you might learn by doing this. And the other one is I think you get a better understanding of what we're doing if you go through it, starting from how I build a synthetic model. To build it, I started by defining some model parameters. We'll get into the details in a little second. Then I proposed some random petrophysical properties, meaning the porosity, water saturation within certain constraints. Then from those petrophysical properties, I can calculate the physical properties, meaning the density of the entire formation, gamma ray property on itself, neutron porosity, resistivity, so on. And then I simulate some field logs based on that. I add some noise, and then we go back, which is really what we want to do, which is really what you would be doing in a real case with field logs. Just to put this into context, modeling is recommended in certain cases, or you can use it all the time, but in some, it's a lot of effort to do it in cases where you don't really need modeling. Just to remind everyone which are the cases where you would actually need modeling. Sometimes if you have thin layers, if you have invasion, if you have anisotropy, if you have deviated wells, these are sort of the obvious. Also, now that we have a more multi-well framework, if you have variation of logging tools or conditions, meaning that you may have wells in the same field that were logged using different tools or different conditions, if you turn them into Earth model properties, they're all in the same space, and you can work with them. You can put them together to get more general conclusions. And lastly, if you're interested in getting confidence intervals, that's what we're going to be focusing on today. And then more specifically, why would you do compositional joint inversion the way we're proposing it here? If you have high salinity, gas saturation, or more generally, if you have any model that is nonlinear, the less linear the model is, the more relevant it is going to be to do what we're doing here. We'll get into that when we reach that point, but just keep in mind that most compositional inversions are done using linear inversion, which relies on the models being linear or being turned into linear. So that's a limitation that we're overcoming here to a point, of course. It's okay. Now let's build the model. We're going to define the model parameters. We're going to say that we have a formation that has thin layers and high resistivity because it's gas saturated, and it follows a shaly sandy pattern. The first thing I'm going to do is define the layer thickness and then randomly assign that layer thickness. I'm going to do that by using a Gaussian distribution that has a minimum and a maximum. So in this case, for example, the layers, I'm saying that in average, they're going to be 0.5 meters. And they're never going to be less than 0.3. They are thin, but not super thin. And here they can have any number, but of course, we're not going to get anything above 0.8. And similarly, I'm going to propose certain distributions for the shale concentration. It's going to be different for the sandy layers than for the shale layers. And I'm going to say that the sand component is going to be 100% quartz, and the shale part is going to be the muscovite. So it's a clay mineral that's going to be part of the shale, and water, always 100% water saturated. The shale itself, not the formation. We're going to have a similar proposal for porosity for shale and for non-shale. And just because we have different shale concentrations for sandy and shale and shaly, the porosity is going to be different in those cases. And the same thing with water saturation. And just last little note, the hydrocarbon fluid is methane. And this is what the model that I built looks like. These are well, you can see the thin layers. Some are a little thicker, some are a little thinner, but roughly uniform around 0.5. The shale concentration, you can see it's almost binary. You have the ones that have high shale concentration, of course, would be the shaly ones, and then you have the lower ones which are mostly sand. None of them are 100% shale or sand. These are the cases. Well, this one seems to be 100% shale. That just happened. That's okay. And then you have the ones that have mostly sandy. They do have some shale, and we see the same patterns for porosity and the same patterns for water saturation. This is the model that we're going to try to recover after we do through the whole journey. And we can do this for multiple wells. I did it for 2. And then I'm going to assign certain rock classes. Remember that in UTEP wells, we assign a rock class is just a label we assign to each layer, and that label is associated to different models. In our case, we're just going to work with the arches or the resistivity model. That would be a better scenario. But all these models can be included, would be different for each one of them. And I'm just assigning them using the table view, just shaly sand, and so on, given the conditions that we gave it. Now, a little side note, now we have, because rock classes are becoming much more important in UTEP wells, now we have a plot that you can use to visualize rock classes. It's very simple. You just add a rock class plot and you choose the colors, and that's it. If you want to make it transparent, you can do that too, but it's mostly just to have a quick reference to see what is shaly, what is sandy. In this case, because it's so binary, it's very easy to tell. But in most real cases, which, by the way, this is also a little bit of an invitation for during the consortium meeting, we're going to have an application of the same thing, but in a field case. And in that case, the distinction between different rock classes is not as obvious as in this case. So a plot like this could be very convenient. Okay, now after we do that, now we have the components, all the petrophysical properties are in place, so we can calculate the physical properties. So first we're going to assume that certain things are known. The salinity is 35,000 parts per million. Sorry, so, I thought somebody had a question. Is that right? You can just speak up. Otherwise, I'll continue. So we have the salinity, temperature, pressure, and we assume that the mineral densities are known. Using that, we're going to use UT-NUPRO or SNUPAR to calculate the nuclear properties, which density is not real nuclear, but it's included here. Neutron porosity, photoelectric factor, and gamma ray. Then we're going to calculate just water resistivity, and using water resistivity because we have everything else. Water resistivity, of course, just depends on salinity, temperature, and pressure, just from these properties. We are going to calculate resistivity of the formation. We can use arches. Remember, this is going to be based in rock class. So for the sandy rock class, we're just going to use arches, and for the shaly, we can use Juhas. Of course, this is not done as frequently. In most cases, you would just play with M and N, but just to show you that even the model can be different, not just the parameters, but the model itself for different rock classes. I'm just going to make it a little bit more complicated than it needs to be, which is fine. And notice that, of course, our Archie's equation is easy to linearize, but Juhas is a little more complicated. Most programs would not be able to handle that. It's up to you. And this is just a quick view of how you would modify the rock class for different cases. You choose the model and choose the parameters. We're going to stay simple 1 to 2 for A, M, and N. So now if you run all that, I've built the physical properties, which is closer to the logs. So we have gamma ray, resistivity, and so on. This is what they look like. They still are pretty binary, as we would expect, which is fine. Then I just run the simulations. There's other webinars about this and other videos we have in YouTube about this. I just made the simulation, and to make it a little more interesting, I added some noise. This was done using the back end, just to make it a little more realistic, to make it a little more interesting. And you can see off the bat which cases are going to be more interesting to model. For example, neutron porosity. You can see that the true property is really far from what you would see in the tool response. So that makes it interesting. Similarly, in resistivity, especially for higher resistivity, is very far off. That's going to be interesting. Okay, so now we've built the model. So we've gone from here to here. Now we're going to go back, just to put it back into context. We're going to try to get the physical properties. So we're going to try to recover this from the blocky logs from the field logs, or the synthetic field logs. If you were to do that, the first thing that you need to have a starting point. In YouTube wells, the easiest way to do it is to do something called populate properties. Sorry, before we go there, so that we know what we're going to match. Remember, going back to here, we're going to try to match the blocky log using the field logs. Now I'm going to start playing with the blocky log because that's the actual property. So to know whether or not we're matching what we originally have right now, I save the properties as a log. We have a module that goes Earth model to log. And this module, of course, can be useful for not only for this part, but to export it to any other program. You can turn any Earth model property into a log set, and then you can save that log set as an LAS and make it compatible with any other program as an LAS. So in this case, I already have these log sets, and I made another log set called true properties that has the properties that were into the original synthetic model that we're going to try to recover. So I just saved them there so that we have something to compare, because we're going to be playing with them. So we're going to be destroying the model, quote unquote. So the result of that is what you see here in the dotted lines, which are going to be permanent. They are actually log sets. Well, sorry, logs. If you look at them, they have a different format, and they are logs. That's okay. Now this is where we're going to start, and really this. If you only had the logs and you were to start doing interpretation, you would start by doing something like the middle of the layer interpretation. At all, you would divide it into layers and then just pick the value that you think is closer to the real value, which is in most cases the middle or something like that. But we know it's far, as I showed you in the previous slide. I did this using this module from UTEP World called Populate Properties. It has changed a bit in the past few years. We made it a little simpler. It's more straightforward. Now it's vertical instead of horizontal. There's less noise. It's easier to choose the properties, and you can also work with radian boundaries, just as a side note. That's how I did it. Now going back to where the reality lies, we see that our interpretation would be really far in certain cases. Photoelectric factor probably is not the best. It's very noisy, and using that algorithm is probably not the best, just because it's very noisy. But for neutron porosity, this would be the interpretation most people would give, and we see it's really far. Same for resistivity. We can see that for density, there's a couple of cases where it's a little bit off, but you don't really need it that much. Same thing for gamma ray. I put it into context where modeling is actually needed and when you don't really need to do it. So now we're gonna start doing that inversion. So we're gonna try to recover certain property. So we're gonna go into UTEP Wells. Now, this is UTEP Wells. It's the same project that I was showing you. Now I'm just looking at the neutron porosity. Let's make it a little bigger. And here, let's see what we have. First, in blue, we have the property itself. In black, we have the log set that represents the true property. So it's where we're trying to get. And then in red is what we're trying to match. Now, we've had this module for a while, so I'm not going to stop too much we've had a similar module for a while. We've updated it recently, but what we're going to do is we're going to run a simulation. And that's going to produce a log. We're going to try to produce, that log is going to be different from the one we have here. Let me do that real quick. If we were to do just neutron porosity in limestone units, which is fine, and we just simulate it, we can get a log set that you can see. I'm going to make it thicker. I'm going to hide the other things. I'm going to hide the properties. This is the log set you would have. Of course, it's very far from the true log set. That implies that the property we have is not right. And all times you would just drag this along. We're going to ignore this. And we're just going to show this. And instead of doing that little by little, we're just going to do it using the MCMC. I'm just going to say run, and then I'll explain what we're doing. We've had this module, like I was saying, for a while, but it's been improved. We have an updated method. It's not completely new. We had it before, but now we've improved it. We call it the biased Latin hypercube sampling, and it's divided into two steps. The first part is something we call the initial accelerated search, which is the biased search. It's biased by the difference between the simulated and the log. Is almost like a derivative-based method, where in that first accelerated search, we're just trying to get the difference between the simulated log and the field log as little as possible. Here we have some diagnostic plots. You can see the misfit, the RMSD, root mean square deviation. They follow the same pattern. They just live in different spaces, slightly different spaces. The lower, the better. That's all you need to know for now. You have a random perturbation, which is dictating how close it's going to get. Then you have two ways to stop the initial accelerated search, either after a number of iterations, in this case I put 20, or if the RMSD as a percent gets below a certain threshold, I put it very low so that it would go all the way through the 20 iterations. Then we always assume there's certain noise. That's important to try to get the match as close as possible. We're just going to assume that is 3% or 0.03 as a fraction. Then after you're out of the accelerated search, you're going to see the label changes here. And what we're doing is we're just proposing different scenarios, different Earth model properties close to what we know the answer is going to be, but with certain variation. That's when the Latin hypercube sampling happens, and that's just is one of the most reliable small sampling methods. One of the problems with Monte Carlo algorithms for this type of inversion is that they just require too many iterations. But we don't have the time. We don't want to do that. The benefit might be too low for hours and hours of simulation. So we need to rely on smaller sampling methods. This is one of the most reliable, and you should get a good assessment of the uncertainty with 50 or so iterations. So here I'm not plotting it right now, but we're gonna see that. Let me start plotting it. In the Earth model, besides just having the line, you can have a confidence interval, and that confidence interval is going to show almost like error bars that tells you what is the lowest and the highest expected value for in this case neutron porosity or whichever property you would be using. Given that you want to include 80% of the you want to have an 80% confidence. In other words, for those people that are more statistics oriented, we have the P10 and the P90. Those are the two limits that we're seeing here. Let me stop it. This is enough. Here in this plot, you see the mean uncertainty, and that just means is the uncertainty. So the range that you have, the difference between the largest and the smallest here, actually using standard deviation. You can also see it as standard deviation. So it's that difference divided by the absolute value. And if you have sampled enough, this is going to flatten out. This is going to stop growing, something like what we're seeing here. You may have a little more growth, but not significant. So I'm going to say that what we have is good enough for the final solution. And now some of the new things that we have is, okay, we can see that as standard deviation. We were able to do that using other algorithms. That's fine. Now, what's different about this one is that instead of just standard deviation, we have a confidence interval because we are generating an ensemble. So a number of cases that are acceptable, and each case has a probability. Without getting too technical, you have a deviation from the property, not just the line. And it's not necessarily symmetric, which is in most cases, most algorithms assume that they are symmetric, which is something you would see with the standard deviation. But the confidence interval gives you a little more interesting results. The reason is most algorithms assume that the final result is going to have a Gaussian shape. We are not doing that, and allows you to see a little more. And something else you can see is now we have a heat map. So you can really see, of course, the more yellow you have is higher probabilities, and the bluer you have less probabilities. And you can change here the transparency. That's what alpha means, so you can see it a little better. Sometimes people prefer to not see the line and just see the confidence interval. We can hide the other. This is what we were trying to get. This is what we're actually getting. You can see there's many ways to show it. Line, no line. You can see that in most cases we're doing a really good job for neutron porosity. We're getting really close to we're almost in every case we're getting really close. And I don't see any case where we don't actually recover. Here we're a little further, but we recover. Here we're a little further and we recover. Overall, that's what you want to see. So I did this for all the properties that we talked about. And now I'm going to switch to another template, and we're going to see the results for all of them. By the way, templates is something that we've been developing over the past couple of years. It's really working a lot better now. It's an easy way to see different layouts of the same well. So in this other template, I have the same results. This is what we were looking at, just neutron porosity. You can see the results for everything. Photoelectric factor is interesting because it has bigger error bars, but it's probably just due to noise. So it's interesting because it's not interesting in a way. That your conventional interpretation would be fine even though you have large error bars. This one is a lot more interesting because it's not the case. By the way, you can see now we have the numbers here that makes it easier. Sometimes they get in the way. It's easy to turn them off. You just click there and you stop looking at them. In some cases, you might want to see them. Now, resistivity is also interesting, and you have this case seems to be really difficult. We don't really get it, which is okay. It's not a perfect algorithm, but it's getting there. It's close, and most of these do get it. And you see clearly where we don't get it, the uncertainties are bigger. If we got a larger confidence interval like 95, which is typical, we would capture a few more, maybe not all of them. We can do 66, which is close to the standard deviation. You can see how that looks. All right, so now we have a statistical description of all the physical properties, not just the blocky log, but confidence intervals. This doesn't mean that you need to do anything more than blocky logs. If you're satisfied with just the blocky log, you can just export it and continue doing your formation evaluation with the blocky log. It's still a better result than just using the log in these particular cases. Now that we have done this, we're gonna go into the joint inversion, where we have this is what the module looked like. I'm gonna close this so that we have less clogged. It's very simple. It used to be a lot more complicated. Now we only have properties that we're going to match. These are all the 5 properties. These are basically the inputs. So what we have here are the inputs and what we expect to get as outputs. So we expect to have a composition. Notice it's by rock class. We have the mineral that we have in the matrix, in the shale, water, the fluid. We have the water in the non-shale. We have porosity. And for each one of these, we have a prior. What the prior is, and this is the only thing that you need to be playing with, but it's not too complicated, is basically the prior is what you expect. It's a probability distribution of what you expect to see. So for example, this one is for porosity. This is the distribution that we are going to use to propose porosities for in our case. So we're saying that it's going to be from here, which is 0.08 to 0.25. These are the porosities that we expect to see. We can make it a little lower, 0.04, for example, up to 0.25. And then this is also a Gaussian distribution. I can play with this directly, or I can also play, this is the sigma, and this is the mu. So it's the mean and the standard deviation. I can make the sigma larger, and that just makes it closer to what we have. Anyway, so this is the space we're going to explore, and this is the probability with which we are going to explore it. Now, I'm going to overlay a histogram. Where do we get this from? We have an expert petrophysicist that knows everything about the field and can give you a good idea. You may have core data. You may have, in our case, we're going to use the inputs that I gave as if they were core data. And this is just a broad approximation. It doesn't need to be as precise. So this is fair. Here, I'm going to overlay a histogram. This histogram is coming from this source. So I'm taking it from the true properties, from the porosity. This is what the porosity looks like. And this is just you can play with the number of bins if you want to look at it differently. This is really what it looks like. So maybe this needs to be centered closer to here. And this seems to take into account all the possibilities. So that will be fine. Something else we can do is now we have the interval of operation. So remember, you can click there. And it's the modeling interval. So basically, it's everything. Instead of that, we could say, OK, because we're working on the sandy rock class, I'm going to say that instead of modeling interval, I'm going to constrain it by modeling. Sorry, not empty selection, but rock class. And I want it to be just the sandy rock class. Now, to make this show, I think you need to select porosity. And you notice that it shifted right a little bit. That's OK. That's because, of course, the sandy layers have higher porosity. So we could probably make the limit, the porosity limit, a little higher, and that would be okay. I'm gonna turn this back to modeling interval, so that the interval operation, remember, applies to anything where we're operating. So when we do the inversion, it would apply there. So we need to make sure it's the whole modeling interval. All right, and you would do the same thing. I already prepared it for everything. So it can be a little tedious. It can be a little time consuming, but it's worth it. You do it once, and it works for all your wells. You can save it and reuse it. Within the project, it applies to the entire project. You can save it and reuse it in other projects, in other fields. That's fine. Okay. So what we're doing with this method is we are proposing, given those priors, we are proposing a number of scenarios. In this case, 2000. Is just the number of scenarios. Is Latin hypercube grid size for the Latin hypercube sampling. We can make it a little smaller without too much trouble. 1,000 scenarios that are going to be petrophysically consistent. That is important. Each one of them is going to have all these properties that are consistent with each other, and we're going to calculate these properties. So we're going to propose 1,000 scenarios, and then we're going to see which one is closest and by how much. And given the noise that we already have, we're going to associate a probability to each one, and we're going to get at the end petrophysical properties, so porosity with confidence intervals. Now, to know how well we're working, we have diagnosis plots. If you click here, they open, and what they show is just the property that you're trying to get. In this case, in blue, the best proposed, just the average of the ensemble for each one of these properties. So we have the gamma ray and so on. Now let's actually run it. Now let's run it. It should take roughly about 40 seconds, something like that. It's going to tell you how long it's going to take. It's going to run UTNU Pro and Archie's equation, or the resistivity model that you have for each one of the rock classes present in here, and then find the solution. So it finished in 26 seconds. It's 1,000 cases, and you can see how close you saw that it changed a bit. That's fine. You can see the proposed, how close the proposed system, how close is it to the actual solution. You can see it's really, really close. That means we should be doing a good job. So to see if this did actually do a good job or not, I'm going to show you another template where we have the petrophysical properties. This is what they look like. Now we have the shale concentration along with the shale concentration in black, which is the true case. We have the porosity and water saturation. So in most cases we do fine. There are certain cases where we don't. It seems like when it's very shaly, we're not doing a great job, especially in water saturation. It might be we need a little more sampling. It might be something else. We do a very good job regarding shale concentration, and we do a good job in porosity. Now remember, we don't only do this for shale concentration. We don't only get the average, which is what you're seeing as a line. We also get a confidence interval, which looks really good in this case, is very small, and you get a heat map, which is just another way of looking at that confidence interval. I'm using 80 as a standard. Now regarding porosity, we can see the heat map and we can see the confidence interval. You can see that the heat map is a little bit choppy, meaning that there's some cases that are disconnected. That's just because I probably undersampled with the 1000. We're going to do it a little more, and you're going to see that those disappear. And lastly, water saturation. Let's show the confidence intervals and the heat map. Something good about this is that in this case that we're not getting the right answer, or what we're expecting to be the right answer is not all that close. We still get it within the confidence interval, and something similar happens here. It's a little off, but not by too much. This one is completely inside in most cases. So if we're not doing a good job, the program tells you where it's not doing a good job, so revisit this. We're getting too high confidence intervals or the confidence interval is too large, so maybe there's a problem in this layer. That's how you should interpret these very high scenarios, and it's only in water saturation, which is good. You don't see that in the shale concentration. That should be fine. All right, so lastly, let me just run it one more time. I'm gonna make it a little, let's make it 2000 so that it runs 2000. So if it took 25 seconds, it should take about 50 seconds to run, and we're gonna see slightly different scenarios. And also, because you see that in the diagnosis plots, the layer that is not being represented as good. In the diagnosis plots, you see that you're matching everything. That tells you that the algorithm is working okay. It's matching what it's supposed to match. There's something else that's not right, and that's up to you to see where that problem's coming from. And now you saw that it changed a little. I don't know. It might have improved. It was tough to beat what we already had. And now you see that the results are, I think this got a little higher, but not too much. It's fine. This, I think it was outside, now it's inside. You see small changes, and it took 45 seconds, something like that. So not too bad. This is it. So let's go back to the presentation. And if there's any questions, please go ahead. And I just had some slides with the results that you already saw. And I do want to touch base on the main features of this algorithm. There are no limitations on the rock physics models, meaning that resistivity can be dual water or any model that you might be interested in using. Same thing for Sonic. We ignored it in today, but Sonic this is already taking too long. Sonic would add, you would do the same thing, and you could use any model you want. Nuclear properties are using UT Pro with no approximations, so neutron porosity is going to be fully calculated. Some other programs they assume linear, so in some cases like high salinity or gas saturated, they're not going to do a good job. In this case, we should do a good job. The ensembles are petrophysically consistent, so all the results that you see are consistent across each other, meaning that the shale, within that set of solutions, there is a shale concentration that corresponds to a porosity for every single case. This is important more in the back end, let's say, but this is very important. The number of outputs is not tied to the number of inputs. Some other programs also you require to have as many inputs as outputs. In this case, we could have just removed the inputs and get a different result. The results include always confidence intervals, which is also, I think it's very specific to us. The method can be seamlessly run in multiple wells. You can, everything we did about the priors and the rock classes would apply to all of them. And it's fast. It's not instantaneous, but 25 seconds is not bad. And that's per rock class. It takes actually a little less than that. It took less than that. We were working with 2 rock classes, so depends on the number of scenarios that you want to propose, but it should be done under a minute, which means that you can test different things relatively fast, and that's all about UTEP wells. That's what UTEP wells is all about: testing different scenarios relatively fast. Now this is probably the biggest highlight of this new method, that it takes short time. We had a method before that took a little too long. When you start going into tens of minutes, that you can go get coffee once, and after that, not great. But 25 seconds is fine. And with that, thank you. I'll take any questions or comments. This was done all with the version 2023.35. It's available. Just send an email if you want to have it, or if you need new licenses. And lastly, this is also an invitation for the consortium meeting. We're gonna go a little deeper into the methods. We have a couple of talks, proper talks. We have a demo that is going to be using field data. And I hope you join us too. And with that, I'm open for questions, comments. I think you can just speak up if you want to.
Thanks for the presentation, Joaquin. If you run the MCMC to do the inversion after the Latin hypercube sampling, does it improve the inversion results for like the resistivity and the neutron?
Yes, it can improve the results. Yeah, if you run it, let's say you're going to run it after you've already run this. Is that the question?
Yeah, so like you ran this step initially, and then you did another run where you were trying to where you ran the Latin hypercube again with from like when you changed from 1,000 to 1,500
Oh yeah,
sample size. And so if you go back and run this now, does this improve the results given that your blocky log improved?
yes,
what
that's
I'm
right.
asking.
Yeah, that's exactly right. That's the idea. That if you run it again using if you modify any of these properties and then you try to run the Lighting hypercube, you will get a different result. And that's the idea, that you could improve it that way. You can do that by the property itself, or the model, or the priors. Those are the main three. And each one of those, of course, it's has a lot of ramifications. Yep. Thanks for your question, Jamie. All right. It seems like some people are asking questions in the chat. Anybody else has questions? Otherwise, we can stop it. But if you have any questions or later, you can always send us an email. If you want to get the software, also send us an email. And that's it.